The universe is filled with vibrations. Everything from the smallest particles to the largest galaxies hums with a unique frequency. Now, a new and exciting idea called quantum resonance field theory, or QRFT, suggests that these vibrations are more than just random noise. They are, in fact, fundamental to how everything is connected. At the heart of this new theory is a number, a constant of nature we call the resonance field constant, or simply HR. This constant proposes that there is a fundamental unit, a smallest possible step, for the resonance that links everything together. It's a new character in our cosmic story, one that might help us understand the deep harmony of the universe itself. Imagine you are tuning a guitar. You can tighten or loosen a string to change its pitch, its frequency. But what if you could only change that pitch in tiny, fixed steps? You couldn't just land on any frequency you wanted. You would have to jump from one allowed note to the next. This is precisely the idea behind the resonance field constant. It suggests that the communication between particles, the very fabric of their connection through resonance fields, is not smooth and continuous. Instead, it is quantized. It comes in discrete packets, and HR is the value that defines the size of these packets, the smallest possible change in resonance you can have. This concept might sound familiar, and it should. It echoes one of the most profound discoveries in science, Planck's constant, which we call H. Over a century ago, Max Planck discovered that energy itself is not continuous. It comes in little chunks, or quanta. This insight gave birth to quantum mechanics and changed our view of reality forever. The resonance field constant, HR, is like a cousin to Planck's constant. While Planck's constant governs the world of energy, HR is proposed to govern the world of resonance. It sets the fundamental scale for the interactions that bind particles together through shared vibrations. So, what is a resonance field? Think of it as an invisible web of influence that connects particles. When two particles are in resonance, they vibrate in harmony, like two perfectly tuned tuning forks. Their fates become intertwined, a phenomenon we call entanglement. Quantum resonance field theory proposes that this connection is mediated by a field, and HR is the rule that determines how this field behaves. It dictates the fundamental resolution of this cosmic web, the finest detail in the pattern of connections that makes up our reality. It's the key to understanding the music of the quantum world. To understand the role of HR, let's look at a simple equation. In standard quantum mechanics, the energy E of a photon is related to its frequency f by the famous equation E equals h times f, where h is Planck's constant. This equation tells us that energy comes in packets whose size depends on their frequency. Quantum resonance field theory proposes a similar relationship for the work, W, required to change a system's resonance state. This work is given by the equation W equals HR times delta nu, where delta nu represents the change in resonance frequency. This means that altering the resonance between two particles isn't free. It costs a specific amount of resonance work, and HR sets the price. This idea has profound implications for how we view the universe. Just as Planck's constant revealed that energy levels in an atom are discrete, like rungs on a ladder, HR suggests that resonance states are also discrete. Particles cannot just resonate at any arbitrary frequency with one another. They must occupy specific, allowed states of resonance. The jump from one state to another requires a precise amount of influence, as defined by HR. This constant, therefore, introduces a new kind of quantization to the universe, the quantization of connection itself. It draws a clear line between states of harmony and states of discord. What's truly fascinating is how HR connects the abstract world of resonance to the physical world of geometry. The theory suggests that the shape, or geometry, of a resonance pattern between particles is directly linked to its frequency. A simple low-frequency resonance might correspond to a simple geometric shape connecting the particles. To create a more complex, higher-frequency resonance pattern, you would need to invest more resonance work, making a jump to a new state governed by HR. In this view, quantum entanglement is not just a strange correlation, it is a physical geometric connection whose structure is defined by these quantized resonance frequencies. Let's make this more concrete with a simple example. Imagine two entangled particles. Their basic resonance state could be represented by a simple line connecting them. According to QRFT, to shift them to a more complex state of entanglement, you would need to apply work. Let's say this work is exactly 1 unit of HR. This might change their resonance pattern from a line to a helix. The energy needed to make this specific change in the geometric pattern of their connection would be precisely determined by HR. The constant becomes a bridge, linking the mathematics of frequency to the physical geometry of entanglement. One of the oldest mysteries in quantum mechanics is the quantum jump. When an electron in an atom moves from a higher energy level to a lower one, it seems to do so instantaneously, without traveling through the space in between. It simply disappears from one orbit and reappears in another. The resonance field constant, HR, offers a beautiful new way to think about this. A quantum jump might not be a jump through space at all, but a rapid change in the resonance state between the electron and the nucleus. The system shifts from one stable resonant pattern to another, and the transition is governed by the discrete steps defined by HR. This idea isn't just confined to the strange world of atoms. It could extend to the processes that enable life itself. Consider photosynthesis, the remarkable process where plants convert sunlight into chemical energy. This process is incredibly efficient, far more so than any human-made solar cell. Biologists have long suspected that quantum effects are at play. QRFT suggests that molecules within a plant's cells might use quantized resonance states to transport energy. A photon of light is absorbed, and its energy excites the system, allowing it to jump between specific resonance patterns to guide that energy with almost no loss. The efficiency of biological systems, from photosynthesis to the way birds navigate using Earth's magnetic field, might be explained by these optimized resonance pathways. Nature, through billions of years of evolution, may have learned to harness the rules of resonance set by HR. It could have built molecular structures that have precisely the right shapes and properties to create stable resonant highways for energy and information. The discrete nature of these states enforced by HR would prevent energy from leaking out into unwanted vibrations, ensuring it gets exactly where it needs to go. Life, in this view, is a master of quantum resonance. So the importance of HR is vast. It promises to do more than just refine our physical theories. It could provide a fundamental explanation for the quantum weirdness we observe, like quantum jumps, by reframing them as shifts in resonance geometry. More than that, it could unify the physics of the very small with the biology of the living world. It suggests that the same fundamental constant that governs the entanglement of particles in a lab could also be the key to understanding how a leaf converts sunlight into the energy that sustains us all. It's a profound and unifying thought. If this new constant, HR, is real, then it must be measurable. We can't just dream it up. We have to find it in the real world. So how could we design an experiment to detect it? One approach would involve carefully controlled systems of entangled particles. We could try to influence their resonance state using precisely tuned electromagnetic fields. By observing the minimum amount of energy or work needed to force a change in their entanglement, we might see evidence of discrete steps. If the system only changes its resonance when the applied influence reaches specific quantized thresholds, we could calculate the value of HR from those steps. Another promising avenue lies in the field of condensed matter physics, studying materials at very low temperatures. In these exotic states of matter, quantum effects become visible on a larger scale. We could search for collective resonance phenomena within these materials. If we observe that the entire system of atoms can only enter specific, synchronized vibrational patterns, this would be strong evidence for quantized resonance. By measuring the frequency gaps between these allowed global resonances, we could again work backwards to derive an experimental value for the resonance field, constant HR. The universe must show its hand if we know where to look. The first step, even before these grand experiments, would be to estimate a possible value for HR. We could start by exploring its potential relationship with other known constants of nature, like Planck's constant, the speed of light, and the gravitational constant. Is HR a completely new independent constant, or is it a combination of the constants we already know? Answering this question through theoretical work would provide a target value for experimenters to aim for. It would narrow the search and tell us whether to look for its effects in high-energy particle collisions or in the subtle whispers of low-temperature systems. The journey ahead is long but incredibly exciting. The first task is to develop the mathematical framework of quantum resonance field theory more fully. Next, we must propose specific testable experiments and estimate a plausible range for HR. Finally, we must look for its signature in the cosmos and in the intricate machinery of life. The discovery of a new fundamental constant is the rarest of events in science. If HR is confirmed, it would not just add a new number to our textbooks, it would signal a profound shift in our understanding of reality, revealing a universe that is not just quantum, but deeply and fundamentally resonant.